Okay, so today we're going to get started with line integrals. And so we're going to have the definition of the basic line integral here. And that's what we're going to talk about right at the beginning here. So we're going to suppose that we have a curve C in the plane, and it's given by these parametric equations, x equals x sub t and y equals y sub t, t going from A to B. That's an A there. So that C is given by this vector function, and assume also that C is a smooth curve. And remember, that means that R prime of T is continuous, and R prime of T is not equal to the zero vector on this interval from A to B. And what we're going to do is we're going to divide the closed interval from A to B into n subintervals, tk minus 1 to tk, of equal width, delta t sub k, and that's going to be b minus a over n. And we're going to let x sub k equal x of t sub k, and y sub k equal y of t sub k for k equal to 1 through n. Then these give you points along C, pk. And so these are those points that you see here along the curve. And these points divide C into subarcs with lengths delta S sub 1, delta S sub 2, all the way to delta S sub n. So like in between P sub 0 and P1, we have one subarc, and the length of that is delta S sub 1. The length of the arc in between P1 and P2 is delta S sub 2, and so on, all the way through. And what we're going to do is we're going to take P sub k bar to be x sub k bar, y sub k bar, be any point in the kth subarc. So here you have this kth subarc in between P sub k minus 1 and P sub k, and we're just letting P sub k bar be any point along this part of the curve. And this point is going to correspond to some tk bar that's in the interval from tk minus 1 to tk. And we're going to assume that f is a function of two variables whose domain includes C. And so then we're going to form this sum. So we form this sum, and it looks kind of like a Riemann sum. We've got this function of two variables, though, and then we have the delta S sub k instead of, like the delta x or the delta x delta y. So, which is similar to a Riemann sum. We then take the limit as n goes to infinity to obtain the line integral. All right, and so here we have this. So this is definition 1. So we're going to let f be defined on a smooth curve C given by this vector valued function as in the above. And the line integral of f along C is given by the limit as n goes to infinity of this sum, if the limit exists. Now, as usual, we don't want to calculate an integral using a limit of a Riemann sum or a sum. We want to have a nice formula for doing that. And so let's talk about what that formula would be. All right, so if we're talking about a line integral in R2, we have two component functions. You can also have line integral in space, but first of all, let's talk about it where we have these two component functions. So suppose a smooth curve C is presented by this vector function A going from T going from A to B with f of x, y continuous on C. Then the line integral f of x, y ds over C. Remember before we talked about the ds when we were talking about the arc length function is the same thing as the speed times dt. So we can replace this ds with the magnitude of v, which is the speed times dt like we saw before. And then along C, f of xy is just going to be f of rt. this vector valued function here, and we're going to let t go from a to b. And so f of the vector function RT is the same thing as f of x sub t, y sub t, and then the speed is just the square root of dx dt squared plus dy dt squared, and then all of that is times dt. And so you might wonder, well, what could this represent? So if f of xy is greater than 0, then you can think of a line integral as representing the area of one side of a curvy fence or curtain. And so if you look at this picture here, you have this curve here in the plane. And then f of x sub t, let me blow this up a little bit. F of x sub t, y sub t represents this height here. And then the ds represents the length on here. So if we take the f of x sub t, y sub t, and we multiply it by this ds, it gives us the area of this, approximately the area of this small little strip. And then doing that at each point along here, we get the area of this curvy strip here. And so you can think of it as representing the area of that curvy strip there. That would be one application of it, right? And we can also talk about line integrals in space. And so actually, let's do that. So let's suppose we have a smooth curve C in space is given by this vector valued functions. This time we have an x sub t, y sub t, and z sub t as our component functions, t going from a to b, and that f of x, y of z is continuous on C. And remember, this is a smooth curve, meaning that the derivative is continuous and not equal to the 0 vector. So then similarly to the line integral in the plane, it's just going to be equal to f of r of t times the speed times dt. So the ds is the same thing as the magnitude of v times dt. And in this case, we have f, we have three components. So we have f of x sub t, y sub t, z sub t. And then the speed is going to be the root of dx dt squared plus dy dt squared plus dz dt squared. And then all of that is times dt. And so this is the definition for a basic line integral, either in the plane here or in space. And so we're going to look at examples of both today. All right, so this is going to be example 1. So we're going to evaluate this line integral along C. We're going to have 2 plus x squared y ds, where C is the upper half of the unit circle with counterclockwise orientation. And so R of t, in this case, is going to be cosine of t, sine of t. And you can have 0 is less than or equal to t is less than or equal to pi. So this is your curve C. And so if we look at what the curve looks like, here, this would be 1, 0, and this is minus 1, 0. And then we're going along here like this. This is your C. All right, so if we look at our line integral, we're going to have, according to our formula, we're going to have, remember the formula is this, we're going to have the integral from A to B, we're going to have f of r of t times the speed dt. So we need to calculate, first of all, the derivative and then take its magnitude here. So if we calculate v is the same thing as r prime. And that's going to be equal to minus sine t cosine t. And so if we look at the speed is just going to be equal to the sine squared of t plus the cosine squared t. And that's equal to the square root of 1 equals 1. All right, so then if we look at, in this case, we're going to have the integral over c of 2 plus x squared y ds. It's going to be the integral from 0 to pi. And then if we look at the f of r of t, that means that we're going to replace the x, this is the x is cosine, and y is the sine. So we're going to replace this x with cosine, and we're going to replace the y with the sine. So we're going to get 2, and then we're going to have cosine squared of t, and then sine of t. And then we multiply that by the magnitude of v, which is 1. And so that's just going to be 1 for that one. And so we're just integrating 0 to pi, and then we have 2 plus cosine squared of t sine of t. And so this should be a pretty easy one to integrate. So what's the antiderivative of t of 2?
2t.
Okay, so we have 2t. And what would be the antiderivative of cosine squared times sine t?
Negative 1/3 cosine cubed.
So we have negative 1/3 cosine cubed of t. And then we're just evaluating that from 0 to pi. All right, so we'll just put in the values here. So we're going to have 2 pi minus 1/3 cosine cubed of pi. And then we're going to be minusing 2 times 0 minus 1/3 cosine cubed of 0. And so this is going to give me, the cosine of pi is negative 1, and then negative 1 cubed is negative 1. So this gives me 2 pi minus 1/3 times the negative 1, and then minus 0 minus 1/3. So this is going to be 2 pi plus 2/3. Any questions on this first example? All right, so let's take a look at line integral in space then. So we're going to evaluate the integral c y sine z ds, where c is circular helix given by the equations So we have that. And so in this case, our vector function, we could write it as cosine t is the first component function, and sine of t, and then t. So this is our c. And so remember that the formula is that we have to have f of r of t, and we have to multiply it by the speed. So if we calculate the velocity here, we're going to get minus sine t, and then cosine t, and then 1. And so what's the speed here? We've looked at the speed along the helix before. Did you forget?
1.
So it's going to be sine squared of t plus cosine squared t plus 1 squared. And so, so we get root 2. All right, so then if we have the integral along c of y sine z ds, this is going to be equal to the integral from 0 to 2 pi. And then we have the y, remember, is the sine of t. This is going to be sine t. And remember that z is t, so sine of z is going to become sine of t. And then the ds, remember, is the speed times dt. And so the speed is root 2. So this is going to be root 2 times dt. So we have that. And so well, let's see. So we've got, so this was equal to the f of r of t. And then here you have the speed times the dt. And so we're just plugging into that formula. All right, so we've got, we can pull out the root 2. And then we have 0 to 2 pi of sine squared. And then how do we integrate something like that? Going to integrate it. So remember with this one, we do the power reduction. Is how we would do that.
Right.
So this is going to be equal to root 2 over 2. And then we'll have 0 to 2 pi. And then 1 what?
Minus cosine 2t.
Minus cosine of 2t. So we have that. And so then we can just integrate this now. So we're going to have root 2 over 2. And then we're going to have t minus what?
1/2 sine t.
1/2 sine t? Sine 2t? So we have that. And so at the lower limit, everything is 0. So we're just going to get 0 there. So the only thing that's not 0 is at the top limit. So we're going to have root 2 over 2 times 2 pi minus 1/2, and we'll have the sine of 4 pi. And the sine of 4 pi would be what?
0.
0. So this is equal to root 2 over 2 times 2 pi minus 0. And so that's just equal to pi times root 2. So we get pi times the root 2. All right, questions on the second example? All right. Now suppose that C is a union of a finite number of smooth curves. C1 through Cn. Okay, so let me read through this. So suppose C is the union of a finite number of smooth curves, C1, C2 through Cn, where the initial point of Ck plus 1 is the terminal point of Ck for k going from 1 to n minus 1.
Sassy, hey, let's hey, acting stupid, what's happening? Ready for you back, I'm a savage.
So then the line integral of f along C of f of xy ds is going to be equal to the line integral along C1 of f of xy ds plus the line integral along C2 of f of xy ds. And then we keep on going all the way out till we have the nth one.
It's frozen again.
So we have that. And so the picture, let me draw a picture. Let's say we just have 5 parts. So we have, in this case, let's say we have this part. This part is C1. And then here we have C2. And then maybe C3 along here. And then C4 maybe going like this. And then C5 is, let's say, like that. So this is what I'm talking about here, where we have, this is what we call piecewise smooth. So the individual parts are smooth, but then we have these sort of sharp edges where the curves come together. And so in this particular instance, like if C is equal to C1, union C2, union C3, union C4, union C5, then the integral along C and we have that. All right, so let's take a look at an example where we have a curve that's like this. All right, so we have these 2 curves, and C is the union of these 2 curves. And so if we want to draw a picture of what this would look like, we have the C1 is just a line. You have X equals T, Y equals T. That's just a line that goes like this. And so this is C1. And so C1 is going like this. Here you have the point 1, 1. And then here you have the point 0, 0. So this is just C1 going along the line Y equals X in between 0, 0 and 1, 1. And then if you look at this one, you have X is equal to 1 minus T and Y is equal to 1 minus T squared. So if we eliminate the 1 minus T, we have Y is equal to X squared. And so that's a parabola. But in this case, when T is 0, you're at the point 1, 1. And then when T is 1, you're going back to the origin. So what's happening is that this curve is going like this. So this is C2, and in this case, C2 goes like that. All right, and then we're calculating this line integral over the union of those two. All right, so let's do that. So first of all, this is going to be the integral over C1 of x ds plus the integral over C2 of x ds. And then remember, we need to use our formula here. So our formula, just to remind you, that one. So remember, we have to do this for each one. So we have to put that in there. And so if we look at this first one, the first one we're going to replace the x with t. So we're going to have t. And then we're going to have the square root of dx dt squared plus dy dt squared dt. And we're going from, in this case, 0 to 1. And so in this case, dx dt is 1, and dy dt is 1. So this is going to be the square root of 1 squared plus 1 squared. So this is just going to be root 2 here. And then for the second one, it's going to be more complicated. So here we have the integral from 0 to 1. In this case, the x is 1 minus t. So we're going to have 1 minus t. And then we'll have, again, the dx dt squared, and then dy dt squared dt. All right, so in this case, this is just going to be 1 squared plus 1 squared is root 2. So we're going to have 0 to 1 of t times root 2 dt. And we can definitely pull this root 2 out. And what's the other one going to be? So we're going to have 0 to 1. So when we take the dx dt, in this second curve, we have the x is equal to 1 minus t. So dx dt is negative 1. So this is going to be 1 minus t. And we'll have the square root of negative 1 squared. And then when we take the dy dt, we get 2. We're going to have 2 times 1 minus t times negative 1 squared dt. So we have that. All right, so we can rewrite this as root 2 times the integral of t, 0 to 1 dt, and then plus, here we're going to have the integral from 0 to 1. I'm going to have 1 minus t, and then here I'm going to have 1, and then plus 4. And 1 minus t squared is the same thing as t minus 1 squared, so I'm just going to write it as t minus 1. So I have that. All right, and so what I can do is I can factor out a minus from this one. And so here I'm going to have the root 2 over 2 times t squared from 0 to 1. And the second one I'm going to have minus the integral from 0 to 1 of t minus 1. All right, so this first one is just going to be root 2 over 2 times 1 squared minus 0 squared, like that. And then we're going to have here minus, and then we're going to have actually plus. I'm going to have a minus 1/8. The minus being from this one. And then we're going to have 2/3. And then 1 plus 4. And then t minus 1 squared to the power of 3 over 2. And then we're evaluating that from 0 to 1. All right, so this first one is going to be just equal to root 2 over 2. And then for the other one, when we put in the 1, this part is going to be 0. So you're just going to get minus 1/12. And then you're going to have minus 1/12 times the other one. We're going to subtract it. And when we subtract, when we put in the 0 there, we're going to end up with 5 to the 3 over 2 minus. And so this ends up being just root 2 over 2 minus 1/12, and then plus 5 root 5 over 12. So we have that. Any questions on this example? All right, so far we've been looking at just the basic line integral, but now we want to look at line integrals of vector fields. That's going to be the one that has the more important applications here. And we're going to talk about line integrals of vector fields. Line integrals of vector fields. And all right, so let's suppose F is a continuous vector field. And remember that that means that its component functions are all continuous. Define out a smooth oriented curve C given by R of t right, then the line integral of F along C is given by this one. So you're going to see this notation. You're going to have an F dot dr. So you have this vector symbol over your differential. And what that's defined to be, what this means is that we have the integral from a to b of f of r of t. And we're going to dot this with r prime. And then dt. So it means that. Okay, so a couple things that we need to note about this. So let's note one. If we have f, and we dot this with this guy. So remember that this one is our unit tangent, and then ds. This is the same thing as f dotted with r prime divided by the magnitude of r prime. Remember that was the unit tangent. And then the ds, remember, is the r prime times the dt. And so we can cancel these guys. And we see that this is the same thing as f dotted with r prime. So what that means is that if we look at the line integral over c of f dot dr, another way of writing that is we can write that as the integral of over c of f dot t ds. So these two things mean the same thing. It's two different ways of writing that. All right, and also second note. So note 2. A curve C is orientated if you move in one direction, the positive direction, along C as t increases. And so at times you may have curves that aren't orientated because as t increases, maybe you have something with sine and cosine. And so it could be that you're moving in different directions along the same curve. An example of that would be if you have a curve that like r of t is equal to the component functions are sine t, then as t increases, it's going to be on the line y equals x, but it's going to be moving back and forth on that. So you're not going to be moving in one direction as t increases. So we're talking about an orientated curve, which means that you move in one direction as t increases, and whatever that direction is, that's the positive direction on the curve. That's the positive orientation along the curve. All right, so this is the definition of a line integral, and this is mostly what we're going to be calculating when we think of line integrals. We're going to think of line integrals of vector fields. That's mostly what we do with line integrals. All right, so let's look at some examples of calculating these guys. So we're going to let f of xy equal y x squared. And then we're going to evaluate integral along C of f dot dr for each curve. And so the first one is going to be C1. So for C1, we're going to have R of t is going to be equal to 4 minus t. And then we have the 4t minus t squared. And then we're going to have C2. You're going to have R of t is going to be t. And then we'll have a 4t minus t squared. 1 is less than or equal to t is less than or equal to 4. So in this case, both of these are really talking about the same parabola. And so if we look at this curve here, the t, this is the x, and then this is the y. So we have y is going to be equal to 4x minus x squared. And so if we look at that, that's a parabola that's going to have roots at 0 and at 4. And it's a downward parabola. And so this is going to be at 4. So this is 4, 0. And then up here, you're going to have this point 1, 3. And so if you look at this curve, the C2, in this case, the C2, you're going from 4, 0. So the C2, when t is 1, you're at 1, 3. And then when t is 4, you're at this 4, 0. So we have, in this case, when we go in like this is C2. And then if we have C1, when t is equal to 0, that's starting at 4, 0. And then when t is 3, then you're going up to the 1, 3. And so if we do that in another color, we're going to have going up this way is going to be C1. That's the C1. And so we have opposite orientations along the same curve. So a notation that we use for that is we could say that C1, we could say that C1 is equal to minus C2. That means that we're talking about, they're both along the same path, but we have opposite orientations along the same path. The same path. All right, so maybe that's going to be meaningful. We'll see about that later. All right, so let's start out with C1. So for C1, we're going to have the line integral over C1. We're going to have f dot dr. And so in this case, we're going to have the integral from 0 to 3. And then we're going to have f of r of t. And then we dot this with the r prime of t, and then dt. So we have that. And so what this means is that here we have our x, and here we have our y, and we need to put it into our vector field here. So the vector field is y x squared. So in this case, we're going to have the integral from 0 to 3. And so the y was the 4t minus the t squared. So we're going to have the 4t minus the t squared. And then we have the x squared. So in this case, the x is the 4 minus t. So we're going to have the 4 minus t squared. So this is the y, and this is the x squared in your vector field. And then we're going to dot this with the r prime. So the r prime is going to be, in this case, the derivative here is going to be -1. And then the derivative here is going to be 4 minus 2t. And then dt. All right, so we got to do this dot product. So we're going to have the integral from 0 to 3. And then we're going to have the t squared minus, multiply the -1 times this guy. So we're going to have the t squared minus 4t. And then we're going to multiply here. So we're going to have plus the 4 minus t squared. And then we're going to multiply that by 4 minus 2t dt. All right, so we're going to have the integral from 0 to 3. We're still going to have the t squared minus 4t. And then plus here, we're going to have t squared minus 8t plus 16. And then we're going to be multiplying this by 4 minus 2t. So we have all that. Now, if we go ahead and FOIL this out, or not FOIL it, but multiply it out, we're going to have this. So we're going to have minus 2 t to the third plus 16t squared minus 32t plus 4t squared, and then minus 32t plus 64. So that's the result of just multiplying these guys out. And then let's combine everything. So if we combine everything, this is what we have. So we're going to have the integral from 0 to 3. So we're going to have a minus 2t cubed plus 21t squared minus 68t, and then plus 64. So we have all that. And then we can just use the power rule on this guy. So when we use the power rule, I'm going to have minus 1/2 t to the 4th plus 7t cubed minus 34t squared, and then plus 64t, and then we're going from 0 to 3. And everything's going to be 0 at that lower limit. All right, so we're going to continue with this one. So when we put in the limits here, we're going to have minus 1/2. I'm going to have 81 plus 7 times 27, putting in the 3, and then minus 34 times 9, and then plus 64 times 3 is 192. And so this is going to give me minus 81 over 2 plus 189 minus 306 and then plus 192. And so altogether it comes out to be 69 over 2, which is equal to 34.5. Let me get that one. All right. Questions on that first one over C1? All right, so let's take a look at over the C2. So for C2, we have the integral over C2 of f dot dr is going to be the integral from 1 to 4. And in this case, we're using this different curve here. So now we have the same vector field, the y is equal to x squared, but now we're using the second curve. So now we have, this is the x. So in this case, we're going to have 4t minus t squared, and then the second component is going to become a t squared. All right, so we're going to have the 4t minus t squared, and then the x squared, x is t, so that x squared is t squared. And then we're going to multiply this by the r prime, which is going to be equal to 1. So we're going to have a 1. And then here we're going to have the 4 minus 2t again, dt. And so this one is going to be a little bit less messy. So we're going to have the integral from 1 to 4. And let's go ahead and do the dot product here. So we're dotting these guys. So we're going to have the 4t minus t squared. And then we're going to have multiplying by the t squared by the 4 minus 2t squared. So we're going to have minus 2t to the third. And then minus 4t squared. So we have that. All right, and then let's go ahead and combine these.
Why is it a negative 4t squared? Shouldn't it just be positive?
Should be plus, yeah. So we're going to have the integral from 1 to 4. And then we have a minus 2t to the third. And then we're going to have a 3t squared. And then plus 4t. All right, so we have that. So now we can just go ahead and integrate this. So we're going to have minus 1/2 t to the fourth plus t cubed, and then plus 2t squared. And so let's go ahead and see what we get. So we're going to have minus 1/2. We put in the 4, we're going to get 256. And then 64. And then 2 times 16 is going to be 32. And then we're going to be minusing a minus 1/2 plus 1 and then plus 2. And so this is going to give me minus 128. Adding those together, I get 96. And then we're going to have plus 1/2 and then minus 3. And so we have minus 35 plus 1/2, which is going to be minus 34.5. And so notice in the previous one above, we got 34.5. So in general, if minus c has the opposite orientation as c along the same path, then the integral along the opposite orientation path is the same as the integral along the path with the regular orientation, but with opposite sign. So if you reverse the orientation, you just change the sign on the integral. It changes it to negative. So that's a general property that we're going to see. Questions on this example? All right, so a common way that you're going to see a lot when you're talking about line integrals of vector fields, they're often given in what's called differential form. So we're going to talk about line integrals in differential form. And so what this is going to look like is you're going to have something like this. And so when we have a line integral written like that, it's in differential form. But actually, we can rewrite this in the regular form for a line integral of a vector field. And you can go back and forth interchangeably, kind of like, just like how we have different notations for vectors. We can use the I, J, and K, or we can just use the regular component form for that. So let's see how this works. So suppose a vector field F is, and it's in the plane, so we're going to have M of xy, N of xy, like that. All right, so suppose we have that, then and this is your curve C. All right, so then if we look at the line integral over C, and so this is going to be the same thing as you're going to have the M and then the N. And then you're going to dot this with x prime of t, y prime of t. And so we could write that as and then we could split this up. So we could write this as c and then m x prime of t dt plus the integral over c of n y prime of t dt. But then this is really the same thing as m dx and dy. And so we normally just write this as 1. So we write this as just integral over c of m dx plus n dy, like that. And so you can also go backwards. So you could easily take these steps and just trace it backwards. And so you can go back and forth. So this is the differential form. And you can easily go backwards and put it right back in just the regular vector form. And so we can use these two forms interchangeably. So one thing I want to point out, if you have a vector field in space, so if we have F is equal to P of X, Y, Z, and Q of X, Y, Z, and then R of X, Y, Z. And your curve C is given by R of T then the integral over C can be written like this. So we can write as the integral of C of P dx plus Q dy plus R dz. And so this is differential form for a line integral in space. So we can go back and forth between these two forms. So we don't use the one in space all that much. Occasionally you might see it, but I just wanted to show you that as well. All right, so let's take a look at a couple of problems where we evaluate line integrals that are in differential form. All right, and so this is just a circle of radius 3. And so you have a circle of radius 3 with counterclockwise orientation there. And so we're integrating over that. So it would be easy to figure out what the vector field. So in this case, the vector field F is just going to be y cubed. And then we're going to have x cubed plus 3xy squared. That's your vector field. So we could actually do the same problem the other way, but we're going to look at it just evaluating with this differential form. So in this case, we have the x is equal to 3 cosine t, and the y is equal to 3 sine t. So we have x is equal to 3 cosine t, and the y is equal to 3 sine t. And so the dx is going to be equal to minus 3 sine t dt, and then the dy is equal to 3 cosine t dt. All right, so let's put everything in here. So remember that we have, this is your x, and this is your y. So we're going to replace our x's and y's, and also we're going to replace the dx and the dy. So we have our integral of y cubed dx over c. So this is going to be equal to the integral from 0 to 2 pi. The y cubed is going to be 27. And then we're going to have sine cubed. And then we're going to multiply that by the dx, which is a negative 3 sine t. And I'll take the dt out of everything. And then I have the x cubed. So I'm going to have the x cubed is going to be a 27 cosine cubed of t. And then I'm going to have 3. And then I'm going to have 3 cosine of t. Y squared is 9 sine squared of t. And the dy is going to be 3 sine of t dt. Oh, sorry, the dy is 3 cosine of t dt. So we're going to have 3 cosine of t and then dt around everything. So I'm taking the dt out of both groups. So we have all of that. So what we're going to have here is going to be minus 81 and then sine to the 4th. And what do we have here? So we have, this 3, so we're going to have 81 cosine to the 4th. And then distributing this here, we're going to have cosine squared, sine squared. So we're going to have 3 times 81, and then cosine squared, sine squared. So we have that. And so one thing that you may notice is that we have an 81 that we can take out of everything. So let's go ahead and take that out. So we're going to have 81. And then we're going to have the integral from 0 to 2 pi. So we have cosine to the 4th of t minus sine to the 4th of t. And then here, we're just going to have 3. And then sine squared of t cosine squared of t. And then if you have cosine squared, cosine to the 4th of t minus sine to the 4th of t, do you guys see that that would be the same thing as cosine of 2t? because this is the same thing as cosine squared of t minus the sine squared of t times cosine squared of t plus sine squared of t. And this is equal to cosine of 2t times 1, which is cosine of 2t. So cosine to the fourth minus sine to the fourth, again, is cosine squared minus sine squared times cosine squared plus sine squared. And remember, cosine squared plus sine squared is 1, and cosine squared minus sine squared is cosine 2t. So that whole thing is just cosine of 2t. So here, we're going to have 81, and this is going to be 0 to 2 pi. We're going to have cosine of 2t. And then this part is going to be 3/4 sine squared of 2t. So we have that. And so what we're going to get here is we're going to have 81. And then we'll have the integral from 0 to 2 pi of cosine of 2t. And this is going to be plus 3/8 minus 3/8 cosine of 4t. Using that power reduction. All right, so what this will give us here is we're going to have 81. And this is going to be 1/2 sine of 2t. And then plus 3/8 t. And this is minus 3/32 cosine sine of 14. And then this is 0 to 2 pi. And so in this case, the sine parts are both going to be 0 at 0 and 2 pi. And then the 3/8 is going to be 0 at 0. So the only thing that we're going to get that's not 0 is when we put the 2 pi into this guy. So we're going to get 81, and then this is going to be 1/2 sine of 4 pi is 0. And then we have 3/8 times 2 pi. And then minus 3/32, the sine of 8 pi is 0. So altogether, we're going to have 243 pi over 4. Again. All right, so let's take a look at another example. And so we're going to evaluate this line integral in differential form, where C is the parabolic arc given by y equals 4x minus x squared from 4, 0 to 1, 3. So we've actually just looked at this problem before in just a different form. So we've got that same parabola here. And so this would be at the point 4, 0. And here you have the point 1, 3. And we're going like that. We're going back along from 4, 0 to 1, 3 along the parabola there. And so this would be the same thing as if we have c and then y x squared dotted with r prime dt. So it's really just like what we've done before, but now we're just doing it in a different form. So in this case, since y is equal to 4x minus x squared, that means that dy is going to be equal to 4 minus 2x dx, like that. And so if we have our integral, so we have our integral over c of y dx plus x squared dy, that is going to be equal to, we're going to replace the y with the 4x minus x squared. So we'll have the 4x minus x squared, and then dx, and then plus we're going to have x squared, and then the dy is the 4 minus 2x. dx, and then we're going from, in this case, we're going from 4, 0, so we're going to from 4 to 1. So we have 4 to 1. And normally we take out the dx here. So we're going to have just the integral. And then we can reverse the order of integration by just changing it. So we change it from 1 to 4. And then we're going to have the 4x minus x squared. And then plus 4x squared minus 2x cubed. And then we take the dx out. And so let's see, so we can maybe do some combining and rearranging. So we're going to have a minus 2x cubed. And then here we're going to have a 3x squared. And then a 4x. All right, so we have minus, and then we can go ahead and integrate this. So we're going to have x to the 4th, and then 1/2 minus 1/2, and then plus x cubed, and then plus the 2x squared. And we're going from 1 to 4. And so here we're going to have, when we put this in, let's go ahead and distribute the minus. So when we put in the minus, we're going to have 1/2 x to the 4th minus x cubed minus 2x squared. And so this is going to give me 128, and then minus 64, minus 32, and then this is going to be minus a 1/2, and then minus 1, minus 2. And so we're going to have 128 minus 96. And then minus 1/2 plus 3. And so that gives me 35 minus 1/2, which is the 34.5 again. Which agrees with our earlier result. Okay, so one of the most important applications for the line integral of a vector field is work. So let's review. Remember, we talked about work before when we were just earlier in the class when we were like, you know, let's say you had like a suitcase and you were kind of pulling it along the ground and you wanted to figure out how much you work to do as you pulled it along at an angle. So let's kind of review that basic formula that we looked at. This was earlier in the class when we were talking about the section on dot product. So recall that if a constant force F causes an object to move from P to Q along a line, then the work done is given by the projection of F onto D, where D is equal to PQ. So we're going to look at the magnitude of the projection. That's how much force is in the direction of motion. And then we multiply by the length D. That's how far it moves. And so remember, the formula for the projection is you have F dot D divided by the magnitude of D squared multiplied by D. And then you're multiplying that by the magnitude of D. And so what we can do is we can cancel. We can pull out the scalar and then cancel. And then we're left with the absolute value of F dot D after we cancel the two magnitudes of D. And then because the angle has to be an acute angle, we don't need to have the absolute value. We can make it just F dot D because of the interpretation there. All right, so now what we want to do is we want to kind of generalize that. So now we suppose we want to find the work done by a continuous vector field F in moving a particle along a smooth curve C given by R of T, where T goes from A to B in space or in the plane. And so what we want to do, we could do like a long Riemann sum argument, but we can probably just understand it thinking about this in terms of local approximation for work. So suppose that a force F of R of T causes, let me just make this a little bit bigger. Suppose that a force F of R of T causes a particle to move along a small subarc of C of length delta S. And so here you have this force, F of R of T. And it's causing your particle to move along this small subarc here. So we can't really approximate how much work that is directly, but what we can do is we can think of like the tangent vector and multiply it by ds here. And that's going to be this vector that you see here. And that if the arc is small, that's going to be pretty close to the curve. And then we can use our basic physics formula that we learned before to look at the projection of this F, the magnitude of this force onto this segment here. And then we can figure out how much work is done like that. And so if we look at the work local approximation formula, so remember, we just look at F dot D. It's just the dot product. And so what we're doing is we're taking F, and if we look at the tangent vector, that has the direction there that we want, the direction right at this point. And then if we multiply it by the ds, which is the magnitude of r prime times dt, that's going to be approximately the same as the length of our subarc. And so This has as length 1. And so multiplying it by this, it's going to have approximately the same length as the delta S. And so this is the approximate direction, although you can see the curve veers away from it a little bit, but it's pretty close, particularly if the interval is small. So it's the approximate direction and the approximate length. And so your local approximation for work is going to be F dotted on with T ds. So this is your tangent and this is ds. And that's going to give you your local approximation for work there based on the principle that we saw before and the fact that the curve is not varying too much off from this vector on that little segment. All right. So then adding up all the local approximations and taking the limit, we get the work formula. It's just going to be the integral over C of F dot T ds, which is basically just our line integral that we've always been working with here before. And so that's going to give you a formula that we can use to calculate work. So notice that work is given by the line integral for a vector field F along C. So basically what we're doing this, think about it as like we're doing it for all the values of T going from A to B. And so when we do that, at each one we get a local approximation, and then adding up the local approximations, which is really like kind of like you're taking like a Riemann sum and then taking the limit as n goes to infinity, we get the work formula. So we're adding up the local approximations and taking the limit as n goes to infinity, we get the work formula. So this is just kind of a shorter way of arguing out a formula rather than going through a long-winded Riemann sum argument. All right, so we're going to take a look at one example of calculating work today. So we're going to find the work done by the force field. All right, so we have, this is the problem. And so basically we're just calculating the vector form for the line integral. And so we have F of R of T. Remember, this is your X and this is your Y. So we're going to put those guys in. So we're going to have minus cosine squared. And then we're going to have cosine T sine T for the X and X times Y. And then if we look at R prime, R prime is just going to be minus the sine of T. And then we're going to have cosine of T. All right, so we have everything we need to do this calculation now. So And so we're going to have the f of r of t dotted with r prime of t times dt. And in this case, we're going from 0 to pi over 2. And so we're going to have minus cosine squared of t, cosine of t, sine of t. And then we're going to dot that with minus sine of t, cosine t. And so when we do this, we're going to end up with the integral from 0 to pi over 2. We have cosine squared sine squared. Sorry, cosine squared sine of t. And then here we're going to have another cosine squared of t sine t. And so this is just going to be 2 times the integral of cosine squared of t sine of t. So we have that. So we can integrate this, and we're going to have minus 2/3 cosine cubed from 0 to pi over 2. And so you're going to get minus 2/3, and then cosine cubed of pi over 2, and then minus and so we have minus 2/3 times 0 minus 1, and this is equal to 2/3. So that's the work that's done. And so sometimes people ask, could the work ever be negative? And so, like, for example, if your vector field sort of represents the velocity of wind, and it's more of a headwind than a tailwind, then the work done in terms of circulating particles along the curve is actually a negative, because it's actually like if you were riding your bike, let's say along the bike trail, and you have a headwind, it's actually fighting you. And so the work done by the vector field would be negative in that case. Whereas if you have a tailwind, then the work done by the vector field would be positive, then you'd have positive work. So the work could be either positive or negative. All right, so that's it for today's lecture. Look for another video and some notes from me in the near future. And also we're going to be taking a look at the fundamental theorem for line integrals. So I may give you that video of that over the weekend so you can get a head start on that. Have a good day.